Hey everyone, and good evening. Now the question is, can you hear me? I'm pretty sure you can, so I guess you can get going. Anyway, I've been having some trouble with my microphone, so if it dies during the stream, don't worry, I'll just reconnect it and it should be back up. If it will die again, then I will reconnect again, so yeah. I noticed that my computer is kinda lagging during streaming recently. Well, it always was lagging during streaming, but it was getting slightly annoying, and I guess now microphone troubles add to it, though thankfully last week there were no troubles at all, but like if you were on my Polish stream 2 weeks ago, you know that I had like issues every 15 minutes with the microphone disconnected. So anyway, so I will be changing my streaming machine. Most of the parts already arrived, so hopefully next week I already have a new streaming machine, and most of the issues I see, hopefully you don't see them as much as I do, should be gone, so I'm pretty happy about that. Anyway, so what we'll be talking about today? And well, before we get to that, today's moderator is KrzaQ again. So hi KrzaQ, thank you for being here. If any of you guys have any questions during the stream, then well, just ping this guy and he will let me know about the question. And another thing, there was also a slight change. The question will appear here in this bar. You can see there's a feed there with some information, basic information scrolling. And actually the question and the person asking the question will be appearing there as well before, well, and disappear when the question will be answered. So yeah, that's a slight little change. Now, we'll be talking today about advanced fuzzing, but before I get to that, I will show you how to solve two tasks in played CTF, and that won't take too long. It took me 10 seconds total to solve both during the CTF, so yeah, I'll just show you how to do them quickly. Both were 50-point challenges, so it's rather easy, but I also realized that more wise people are probably watching my stream as well, so yeah, some content for them as well. And after that, we'll talk about genetic fuzzing. How does it work? How does it differ from the fuzzing which I did show you last week, which was, you know, plain old dumb fuzzing, which just randomly chooses a byte and mutates it. Genetic fuzzing actually works pretty much in a similar way. It chooses randomly a byte and then mutates it, but the next step is something a little bit smarter, so yeah, I'll get into that today as well. There's also one more change. Actually, at the end of the live stream, the ending screen, which always contain like blah blah blah, the end, here's some link, will also contain a simple task, a simple, well, I will not use the word challenge, but it might be a CTF challenge worth like, I don't know, 20 to 50 points, maybe more 20 points. Something to, you know, if anyone likes doing some challenges, some simple tasks, it's a somewhat of a crypto, somewhat of a programming challenge, then yeah, just try to solve it, leave the answer in the comment down below, and on my next stream I will, congratulate, obviously, the person who solves it first, and then there are no prizes. At least I cannot think of a prize right now. Maybe I figure something small out later, but at this moment there will be no prizes, and I hope to actually maybe introduce some in the future in the next streams, we'll see. And obviously show how to solve the task as well, so if you approach the task and you're, you know, more novice, you might not be able to solve it, then I'm going to show you how to solve it on the next challenge and on the next stream. So let's show my desktop and let's switch to, do I have a browser? Hello browser. First of all, as usual, this is KrzaQ's website. Again, thank you KrzaQ for being my moderator today and also helping on IRC and so on. Yeah, folks, please visit his blog. He posts some interesting stuff, although he didn't post recently. KrzaQ, please post something new. Then, Live Overflow, as always. I mean, if you're into CTFs and security, you totally should subscribe this channel. Here is the subscribe button. This is actually encrypted for subscribe, if you're wondering what this sign says here. And I did notice he did some RSA stuff, so if you're into RSA, then, or you're not into RSA, but you would like to learn something about cryptography, then check out his newest video. And this is actually, I would like to make a shout out to Marcin, who suggested making the challenges at the end of the video. So, so yeah, thank you, good idea, and I will absolutely use it. Now, if you've been here last week, or if you haven't been here last week, I was talking about basic fuzzing, and you can basically find the source code on my GitHub in the 017 fuzzing basics, which is, you know, just github.com/ginveil/stream, and as in live streaming, and but without the live, so just stream-en. And yes, last weekend there was Plate CTF, which is one of the greatest CTFs during the whole year, created by Plate Parliament of Pwning, which is one of the top, if not the top team, the CTF team in the world. I think, I don't know if they're like top 1 on CTF time right now, but yeah, they are. That's like same old, same old. Basically, I did solved 3 challenges in VA and helped a little in one more, but let's say 3. I did the zipper for 50 points. Yes, 50-point challenge. Down the reversing hole for 50 points. Yes, another big challenge solved. And actually Game Boy for 450 points. I started making a video about it, and I should finish it maybe next week. And yeah, and I'll show you how to pawn it. Basically, the vulnerability itself wasn't. It was somewhat complicated to find the vulnerability, and that was done by KrzaQ from Dragon Sector, and I actually exploited it, and exploiting was crazy, especially that I didn't notice that you have an information leak, and I did it like in a different way. So yeah, watch out for a video. I hope to have it published next week. I'm also actually want to, you know, set up my new computer before I go to video editing, because video editing is also lagging a little on this, especially after the Camtasia updated to the 9th version, which is Camtasia is the software I use for video editing, and the 9th version is somewhat laggy. I hope it actually my new computer will be able to handle it. Anyway, so I'll show you how to solve zipper in 3 seconds. So okay, first I will launch the console, and now it's already downloaded here. So 1, 2, fail, yeah. And this extracted some data, and if I actually cut the data, so if I do cat bin, I have the flag, that's it, yeah. And now what is brute_zlib, because that's obviously like the key to solve this. And this is a small tool I've written some time ago in hope that I will find it useful. Actually, after I played the CTF, I changed my font size in Vim. I need to fix it for today, so please give me a moment while I actually uncomment my config for live streams. I should have done it before the stream, I'm sorry about that, so yeah. Okay, now the font is sufficiently large. So what does it do? Actually, it uses like imports zlib and then tries to decompress the data that is passed to this. And it tries to decompress it normally, and then it tries to decompress it with like this weird -15 parameter. -15 is actually, it suggests to use a version of zlib. That's not true. Like, it suggests to use a certain setting for zlib, which doesn't require a certain header, and this is actually how zip uses zlib. And it tries to just return the data, and then it actually does a brute force on the data, which means it goes byte by byte, it grabs some bytes from the file, so as you can see, like 128 bytes, so not a lot, right? And then it tries to decompress it, and if any data was successfully decompressed, then it just outputs it. So that's it. It's just like brute forcing zlib. Every byte in the file is treated like a zlib compressed stream, and it tries to brute force it. So it's perfect for this kind of challenges. However, since this is, you know, an educational stream, I am going to show you how to properly do it. I actually did it after the CTF, since one of my teammates did ask me about it. So it's a zip file which is corrupted, and you have to uncorrupt it, right? So I'm going to use Hex Workshop for it. Hex Workshop has actually this magical thing which is called structure viewer, and I can select the structure library, and I can select zip format. It actually comes by default, it's not something I created. And then I can click here, add structure, and there is something local file header. I don't know if you can see it, but there is actually a checkbox. Well, I don't know how you call it, like a check sign next to the local file header. If you know the zip file, local file header is just what you expect to be at the beginning of the file, not because the standard says it should be at the beginning of the file, but that's how usually it goes. And here's the weird thing about this. It actually marks where the structure is located, and the local file header is a small structure. And it contains also the data of the file, but obviously the compressed data cannot be in the whole zip, and so, but for some reason it tries to like, it tries to tell me that, hey, it's actually in the whole zip file and even further down, because there is no like red border at here, so it's, yeah, out of bounds, right? What's up with that? So, going through these parameters, you can actually notice that the compressed size is okay, the compressed size is probably okay. File name length, 9,000. Well, no, it's over 9,000. As you can see, it's plainly, I think that was even the joke intended here, that it's over 9,000. So I don't think the file name was supposed to be over 9,000. Now, the file name is actually placed here, right? And it's marked it here, and you can see there are like 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then there is like UT, blah blah blah. UT, it's commonly part of the extra field where there are some data. It's not always, it's like, if you see UT, it might be part of the extra field, and this is like a heuristic I'm using. It's a rule of thumb, not a clear rule, which means that probably like these 8 bytes, do I count correctly? Sorry, or was it these 8 bytes? Yeah, these 8 bytes make up the file name. So I'm going to change the file name length into 8. And now I need to actually click, right click on it, and there's something like refresh all structures. And now I refreshed it, and it's more sensible, and especially it's more sensible because it stopped before the next PK. PK is the magic of a chunk, basically, of a header in zip. So a zip file is made of chunks, if you will, and each chunk starts with PK, and then there is like a 2-byte magic value which says what type of a chunk is it. And this should be probably the central directory or something. So I'm going to again right click it, click add structure, and then, yeah, it's a central directory file header. So I'm going to apply it, and again, here's the same story, right? The file name is like over 9,000, so I'm going to again change it to 8, and I'm going to refresh all structures, and it's fixed, but now I need to fix the file name again, so I just go here, select, oh, you cannot see it, probably. I'm sorry, let me make it like this, yeah. So I selected file name, it showed me that the file name should be here. So I'm actually going to override the file name with something else. So 41, well, no, that's not what I meant. I meant A. And I'm going to do the same in case of the previous header. So that would be file name here, A. No, not like that. Yeah, like that. Okay, now I'm going to save, and I think that's actually it, and I should be able to decompress the file now. I'm going to actually spawn the Linux console since I have an unzip here. And zipper, yeah, and it properly inflated it, so that was the way you should do the task, and not like brute force all the zip streams in the file as I did. And the second challenge, which I also solved in like, I don't know, 7 seconds, and I'm not really exaggerating, even, is like the down the reversing hole. You actually get an exe file. Let me maybe show you. This is this exe file, so this is a hex editor view, and it's fishy from the beginning, because you know you expect it to have some a DOS stub. Where is the DOS stub here? But if you go like, if you scroll a little lower, you can see that there is this like, this program cannot be run in win mode, whatever, but there's some stuff here as well. So my first thought was, somebody actually replaced the DOS tab with some proper DOS program. So what I did, I went to my Total Commander, and I clicked this icon here, which is DOSBox. And DOSBox opened, and I did like reverse, enter, and I got the flag. And that was it. Yeah, here you can see the flag. So this whole task was about actually noticing that somebody played with a DOS tab, and thankfully that was the first thing I checked. So yeah, but again, these were like 50-point challenges, so don't think too much about it. I'm still happy that I did notice the DOS tab, and I'm still happy that my brute force zlib finally did come in and was useful. Yeah. Okay. So what do we do now? We now talk about fuzzing, and that's the advanced fuzzing. So, I'm actually going to show you, write actually an example of a, let's call it a parser, but it's actually just a test for a fuzzer. And I'm going to tell you why this example is a nasty example for dumb fuzzers and why genetic fuzzers. So now let's start. It's going to just read a file. I guess I should like provide the name here, argc, argv, then I do an fopen on argv1. So just standard file opening. If the file is not here, then return 1, and then do an fclose at the end because we are nice. And now let's read, I don't know, let's read some bytes. So I'm going to call it char buff. It's not going to be a buffer overflow, it's just a test. Maybe 16, because why not? And I'm going to initialize it to 0. This actually initializes the whole buffer to zeros, because what the standard says is that if you initialize only part of an array, then the rest of the array is initialized by default values, basically, which means 0 in this case. Now I'm going to read it into it, 16f. Okay, and now I have this in my file. Now I'm going to do something like this. And this is basically a simulation of a really advanced file format parser, which is done in a not an advanced way. If the first sign is A, then if the second sign is B, I guess you can see where this is going, right? If the third one is, and so on and so on. I actually don't going to do these. Yeah. And I need to do this like 15 times, let's say it. Yeah. Blah, 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 blah. 10, I need a couple more, sorry. My English today is terrible for some reason. Maybe because I'm tired a little, I don't know. Yeah, and now I'm going to put some magic values here. It's actually going to be the alphabet. Can I write the alphabet? Let's see. No, it seems I cannot write the alphabet. I'm sorry. I'm going to just write random letters in that case. OP. Okay. And now, if all these conditions are met, I'm going to crash the program. Yeah, just crash it. And I'm going to crash it by doing... How am I going to crash it? I'm going to crash it like this. 0 int. Yeah, this should crash the program. Now I need actually a whole bunch of closing brackets. Vim is actually helping me. How nice of him. Did I finish already? How many are there? There should be 16. It's 16. Perfect. Yeah. So it's like basically an emulation of, think of a complicated parser which has a bug somewhere there, and the bug is actually here, right? And to get to the bug, you need to select proper options from the file format. Like in the file format where, there are headers and everything, you need to select like proper values everywhere. Like in the first header, you need to set this flag. In the second, you need to set this. In the third header, you have to set like 5 flags differently and put like proper values everywhere. And then in the end, if you set everything correctly, you reach a certain state in the program where the bug actually triggers. And yeah, and this is actually the simulation of a state. I'm going to now compile it. Perfect. Does it work? It works. It doesn't crash, obviously. And if I need to give it a file, I'm going to I'm going to call the file test. I'm going to put some A's only in the file. Let's see if it crashes now. So A, and the file name is test. No, it doesn't, and now I'm going to test it. Okay, and now it crashes, and my, just in time debugger shows up, which is perfect, which is what is expected. So now let's assume that we start fuzzing, right, with a dump fuzzer. I'm going to actually copy the dump fuzzer I created on the last stream. What do I need? I need this. Yeah, I think I need only these two. Okay, so I copied my GDB script and I did copy my fuzzer, right? And what I need to do is I need to change certain, like input sample is called test. No, I'm just going to rename like copy test into input sample. And I think that's about it because, yeah, because my program is called exa anyway. If you don't know what this code is, basically just watch last video, but it's pretty easy. And I'm going to start my fuzzer on it in hopes of actually finding this condition and crashing the program, therefore finding the bug. And how do I even start this fuzzer? I'm going to just do this. Yeah, and and I do have this, you know, like GDB is kinda spamming my screen, but that doesn't matter. In the end, this will not be able to find my the issue. And even if I, you know, disable the GDB, because GDB slows it down, and last time when normally in fuzzing, you wouldn't run the target through GDB, you would run the target, and if it crashes, then you would actually attach, run it again with the same sample on GDB. And so therefore I'm going to change it a little, I guess, to not run it through GDB again, or am I going to, no, I guess I'll leave it as is. So yeah, and anyway, the fuzzer will never be able to find this bug, and this is why. Because, well, this is our input file, right? It's like 36 A's. Now what the fuzzer does, if you remember correctly, it chooses one mutation algorithm, for example, mutate bytes, and then it chooses like how many bytes will it mutate. Well, it obviously is 36 times this, so this is 0.36, which isn't too much, which is 0 actually if you cast it to an integer. Therefore, it will just mutate 1 byte, and it changes randomly 1 byte. So let's say that it's lucky enough to actually hit the second byte. Well, nothing happens, right? I mean, the application doesn't crash. The application, to crash, you would need to hit all the 15 bytes, which doesn't happen. But, so what does this do? Well, it basically retracts the original sample and mutates some other byte, and it could put J here. But again, nothing happens because to trigger the bug, it needs to, well, get all these conditions correct. And it will never be able to trigger this bug, because it will never mutate more than 1 byte, and therefore it will never hit the combination. So let's say we actually increase this, right? Let's say we increase this output 0.1 to actually mutate half of the bytes all the time, or even all of the bytes. Why not? We have a good day, let's mutate all of the bytes. What's the probability of hitting the correct bytes? Well, it's obviously it's only, you know, lowercase letters, but it actually does mutate bytes, it doesn't mutate letters. So it's 256 to the power of, how many did I say? 15, right? So this is the number of iterations it would need to go. And let's assume that we are using actually a super fast fuzzer. Our fuzzer, my fuzzer, which I've written, is slow, is really slow. It's like 1 execution per second. That's not good. Modern fuzzers can do 1000 executions per second. So that's let's divide it by how many executions per second it can do, and then let's see how many years it actually is. So that's how many seconds are in a day. That's 86400, and there are like 365 days in a year. So that's only this many years to actually until we find the bug. So that's probably not going to happen, right? Even if we mutate all the bytes. Therefore, this is not the proper way to go about finding bugs. And I guess welcome to Michael Zalewski, when he was implementing American Fuzzy Lob, I think it was his idea. He decided that there's a smarter way to actually go about it. What he did is, let me actually open the file in IDA. I'm actually not going to open the test file itself. I'm going to do something else. I'm going to do -C to have an object file, because this is a useful trick if you're learning reverse engineering. If you're learning reverse engineering, then just basically compile something to an object file, because in an object file you have everything Oh, sorry, again, I need to fix my fonts. Yeah, because in an object file, you don't have all the prologues, epilogues, you have all the symbols, and so it's easier to just focus on assembly code. Anyway, so this is our main file, and our main file actually looks like this. This is a graph, a huge graph, right? Now, what I'll come to figure out is that, hey, if my mutated sample actually, usually the samples just go here, right? And then they take this green route here, this one, which means that AL, the first byte, is not equal to A, then it will go here, which is, well, this exit part, basically, right? So the application normally goes here, the application normally obviously hits this block, and obviously the application also normally is, well, goes to this block, right, which is the beginning block. Now, let's assume that suddenly the application on the second position, on the first byte, it hits A. Well, that's okay, right? It normally hits A, so it also goes here. And then it compares the B. And then the application, well, suddenly hits B, and therefore goes to the next block. Now, what a dump fuzzer would do at this moment would be, well, whatever, discard it, and that's it. Now, what AFL does, AFL actually sees that, hey, we just reached a new block in the graph. We were never here, so this sample we mutated, we actually keep it. We actually add it to our corpus of samples. And therefore, the next time we pick a starting sample to mutate, we can pick this sample, which we know it hits this block. Therefore, it will actually, have in the corpus, it will have a sample which has A letter, B letter, and then again A, but it knows already that it can hit here, this block as well. So then at some moment, this sample is again picked from the input corpus and mutated, and suddenly he hits C. Therefore, this condition is met, and therefore he goes to this block, right? The fuzzer, I mean. So, and since it reached again the new block, it says, hey, I was never in this new block, therefore I found another sample which I need to add into my corpus. So it now has like A, B, and C, and then the rest are A, but it already has this and keeps it in the corpus. And now it goes like repeats the process again and again and again and again, and it actually, like, after some time, it reaches this, like a sample which can reach this block. And then it actually like randomizes, the mutator randomizes P at the end at the proper position. It obviously might take some time, and it reaches, well, this block, and this block actually crashes the program. Therefore, by adding samples, mutated samples into the corpus, and mutated samples which do like explore the application more, or actually reach a graph part which was never explored before, well, then it's worth to keep it, and thanks to that, and thanks to mutating samples like that, in the end you do reach the, well, some areas of the application which was not explored previously, and therefore were not fuzzed previously. And if you can fuzz such areas, maybe there are bugs hidden. There might be no bugs there, obviously. I mean, through most of this graph, right, through these many nodes, there are no bugs. But in the end, when it did, like, the final mutation, it did reach this state, and it would crash the application. So this is actually called genetic fuzzing. And why is it called genetic fuzzing? Because if you know genetic algorithms, they work in a similar way. You start with with some specimens, right? And in our case, it's just the input sample, the one with which has A, right? So this is the input specimen, and then it mutates it, like same in genetic algorithms, right? You mutate it, you just cross over the samples, and then you see which specimens. Sorry if my pronunciation is incorrect. Again, my English is terrible today. So the specimen basically are better suited to the conditions which are tested, and in this case, in case of AFL, the condition is, did it explore any new, or actually how many nodes in the graph did it explore, did it reach, how many nodes in the graph did it reach? And then it keeps the specimen with basically the samples which are, well, traverse the most of the application. Actually, in terms of fuzzing in AFL, all the samples would be kept, but that's the general idea. And then, like, rinse, repeat, right? So it starts at the beginning where it has the new generation of samples, and it chooses, like, mutates them, or chooses, in case of AFL, just chooses one, mutates it, and again checks if it did explore any new parts of the graph, and repeat. So it's a variation on the genetic algorithms, so therefore it's sometimes called or referred to as genetic fuzzing. Anyway, I do see there are some questions, so I'm going to quickly answer the questions before we get to the implementation. And actually, before we get to the implementation, I need to tell you something more, because I kind of lied about how AFL worked and how fuzzers worked, and I'm going to explain myself in a second. So let's see, what are the questions right now? There are like 7 questions, so let's go quickly through them. Cool. Will I ever show my setup? So depending on what are you asking about, if you want to see my, I don't know, the case of my PC, then probably no. I guess maybe the new one. It's a little more interesting. I can show you how my setup looks like currently. Give me a second, I just need to find the proper link. Oh, here it is. Okay, so let's go to desktop. Oh, now I need to find a browser. Do I have a browser even here? Yeah, I do. Yeah. So yeah, this is my current setup basically. Like for display, I have my camera over here, and here is where my microphone is standing, and that's basically my current setup. Well, this is an old photo. I actually have a different display right now, but I think everything else is, and my desk is a little more messy. And if you're asking for hardware, well, then I have like a 6-year-old Core i7, 32 gigs of RAM, and some other stuff, but yeah, like a generic PC in the end. My new one will be 64 gigs of RAM and 8 core Core i7, like a Broadwell Extreme Edition or something. Yeah, like a computer, basically. If you're interested in more details, then let me know. Okay, the next question. Can students from foreign countries attend Confidence 2017? Yeah, sure. I mean, why not? I think there's also like a discount, a huge discount for students. Please note that there are some talks on Confidence, I think like half of the talks which are actually in Polish, but I think the other half are in English. At least that was usually. Please check the agenda before you actually register. And there's also, the CTF on the conference itself, but you do have to you need to be physically in KrzaQ to be able to play, and let us know basically before, so we make sure there is enough space for everyone. But there are a 4-person team CTF, basically like somewhat a finals, quote unquote. You don't have to qualify, you can just go to the conference and say I'm going to play the CTF, and there will be space ready for you. Okay, next question. Oh my god, the questions are coming, like piling themselves up. We are casting the streaming at work. The whole team is watching you guys. Now I'm scared. Hi everyone. What is the best free hex editor for Windows? That's a good question. So I used, as a free hex editor, I used something called Hexplorer. Here it is. Yeah, and this is it. It's IC's Hexplorer. It has some bugs. I personally do like it though. It doesn't have all the features which Hex Workshop has. There are probably better Hex editors on Windows which are free or open source. If any one of you has any idea, then actually tell KrzaQ, and KrzaQ please put it in the questions so it displays like there on the feed. That's a good question. You have to show the tools in your arsenal, so some of them are still kept a secret because it's somewhat an advantage to our team that we have some secret tools on CTFs. which is not the real reason. The real reason is that the code quality usually sucks, and I am probably going to open source them when I have some time to improve the code quality. There aren't so many tools I use. There are like, I think like 3 or 4 tools related to CTFs or security which I've written, which I'm using. That would be about it. And they're more somewhat like framework-ish, library-ish, not really like something you just run and it magically solves the challenge. Yeah. Why does it run differently when you execute it under Windows, though? Why does it run? I'm sorry. Why does what run differently when I execute it through the Windows? I'm not sure what's the context of this question. So if you could let me know, I'm going to answer your question. Why not do a string compare? Yes, string compare could be that's actually a good question, which I probably should answer. Oh, okay. So KrzaQ says the previous question was about why does the application executes differently when it's run under Windows than when I run it under DOSBox. So this is like, okay, everyone which was born after 2000, this was news for you. Everyone who was born like before like 90s, this is, you know, this. It's basically like this. When Windows was being introduced at the beginning, it was just a program for DOS. You basically DOS was your operating system, and then you type like win, and it executed Windows, which was this interface providing some API, blah blah blah. Therefore, it used actually the same executable format, and the idea was that well, if you have a binary like an exe file under DOS, you might think you can just run it, right? Because that's just an exe file. But some binaries obviously were Windows applications. So what they did was just for the users to include something called a DOS stub. And the DOS stub was executed under DOS, and it was supposed to tell the user, hey, you have to launch Windows actually, and then run this application through Windows to be able to use it. And that was like all the DOS stub actually told you. And that was like a really small program, small assembly program at the beginning of the executable. Now, what Windows applications did was they were using a different type of headers. Like for legacy purposes, there was this old DOS executable header, but then there was something called like, in case of Windows Windows NT and so on, and maybe Windows 95 as well, that was a portable executable header, which was a little further down. And that was where Windows, when you run the application on Windows, that was the part of executable which Windows processed, and that obviously could contain different programs. And I think there was like 1 or 2 applications which you run under DOS, it would actually work under DOS, but if you'd run it under Windows, it would work under Windows. There were like 2 versions of the application basically mixed with one another, but most of the applications just use it as just generated this DOS stub telling the user that it has to be run under Windows. Therefore, this application, when I run it under Windows, it did something like the CTF challenge, right? Because Windows executable parser focuses on the Windows specific part. However, the DOS box is a DOS box, so it focuses on the DOS part and it executes that. So that's the reason it showed the flag. Yeah. Okay, there are some more questions. I'm going to answer one more. Why didn't I use string compare instead of doing this like recursive if loop? And that's actually a really good question. And the answer is easy, because if I would use string compare, this nice graph would not be generated, because it would be just one call, right, to a function, which is basically a loop. And I wouldn't be able to basically explain how AFL works. So that's the reason I didn't use string compare. And actually there are like ideas because when using modern fuzzing, it's great to have, for each state of the application, to have a different graph node in the executable. That's obviously not possible because there are a lot of states in the application, but like only so many graph nodes are possible. But you can actually unroll a string compare or mem compare to such a graph node of like comparing one byte with v next, with v next, with v next, just to give the fuzzer some help where deciding if something was hit or not. Anyway, so I did tell you that I lied a little about how fuzzer works, because I told you that so AFL is like going to this node and then it's noticing that this node was hit. This isn't completely true. What AFL does, it notices these arrows, the edges of the graph. It like checks the beginning node and the end node, and it says, oh, this edge was not yet traversed, therefore I'm actually going to use this edge, this sample which I mutated, as sample which traversed a new edge. And this is important because sometimes you have, you know, these huge switch cases. Oh no, that's even not a good example. Sorry, a good example. A good example would be code like this. Blah, blah. Yeah. If condition A or condition B, then do something, right? If you'd actually do a graph of this code, right, it would be something like this. Here we check condition A, and if it's okay, then we go to ASDF, right? This is ASDF. ASDF. And this is untrue. Now on false, it would actually fall back to B, to checking the B condition. This is false. B. And B might be true and it might go to ASDF, or it might be false and it might like go somewhere else, right? So in this case, if you traverse A and traverse like ASDF, you might say that, oh, I reached already ASDF, so I'm fine, ASDF was always reached. But if you look at the arrows, you actually notice that, well, actually this wasn't, like this edge was never reached, and there might be some interesting application states lying there. Now what I've written here, I've actually written here another node, which is quite obvious that this node is, well, this node will be hit, right, if it's false. So even if we hit this node, that doesn't mean that we do hit this edge. Therefore, looking at edges instead of nodes is a better way to distinguish between possible application states. Now I'm using another term here, which is application state. Now what's an application state? It's actually, the rule of thumb is that the application state is a moment in an application. You do a snapshot in a given moment, and there, like, each variable has a certain state, right, a certain value, and the execution is in a certain place, the stack has certain data in it, the memory, the heap has certain data in it. Everything that is a single state. And for each node actually in the application can have multiple states because, well, first of all, everything around it can have different values. Like when you are here in this node, you have no idea what's on the stack. That isn't interesting for this node itself, right? Maybe apart from like this, because it actually references the stack. But apart from this variable, it actually doesn't care about the stack. But everything still, like, reaching this node is possible in almost an infinite, not an infinite, but almost an infinite amount of states. So that's one thing, and the other thing is actually inside a state, each variable can have only a certain number of possible values, right? So if you look from a different way on it, let's look at this node. This node has only so many possible states which do affect this node. And how many possible states were? Actually 256. How do I know that? Well, because it uses only 8 bytes here, so this is like 256 different values which somewhat affect this application, but that's not fully true because this pointer here, there's also a 64-bit pointer here, so that's 2 to the power of 64. Therefore, we can say that this application actually has like 2 to the power of 70, math is hard, 72 possible states, so that's quite a lot. Obviously, most of the states are like identical in terms of meaning, but fuzzing is basically like going through all these possible states, picking them at random, and trying to see if something crashes. And this method of tracing actually which edge was hit or which node was hit in a graph, in the execution graph, is one way to make exploring this state tree, this gigantic, unimaginably large state tree of the application in a sensible way. Now, I also lied to you by saying that AFL does look at the edges. What it actually does look is, I think it looks at the paths. Maybe I'm lying now, but I think it either looks at single edges. I know some fuzzers do. So, because I'm not super familiar with AFL. I'm more familiar with a fuzzer which I've written, which isn't really external. I've written with Mateusz Jurczyk at Google, and which we use internally. So yeah, so I might be mixing these two things up, but they're somewhat similar. So yeah, so one way is to look at edges themselves, and the other is to take like 5 last edges which were traversed. So for example, this is a path made of 3 nodes, and is like, you can think of it like an edge, but edge has like 2 nodes and this has like 3 nodes. Or you can do it with like, you can say that if a sample went in a different has a different path than a path which consisted of these 5 nodes, then added to the corpus and so on. You can actually do different variations here. What AFL does is actually counts how many times a given node or a given edge was traversed in an application run. So, and there are buckets actually. If I think it is like powers of 2, so it's like 1, 2, 4, and 8. Therefore, if you have a sample which traverses this path, this edge, only once, and you didn't know of a sample that ever does it, you put it in the bucket 1 because it traversed only 1, and then you get another sample. You mutate it, and then you get another sample, and it suddenly traverses this edge like once, and then it goes somewhere and comes back and traverses a second time, blah blah blah, comes back 3rd time, and then 4th time, and then 5th time. So you put it in a bucket of 4 because it's actually like 4 to 7, right? And this is like 1, 2, 3. Yeah. And you put it in this bucket, and you keep it in you add it to the corpus because, well, you never had a sample which you could put to this bucket. And Michael says, Elkamtov says that this actually doing this bucketing on how many times each edge was traversed did some good results for AFL. Okay, looking at the clock, I'm not sure we can implement the genetic fuzzing today, but at least I'm going to tell you how to put this theory into a practical approach. I'm going to go through a couple of questions, maybe 2 questions now, and then I'm going to give you some hints on how to implement it, and maybe next week we can actually implement it and focus only on the implementation instead of going through theory as I needed to do today. Okay. So there's a question. Have Gen been on Tyler's talk on Insomniac about automatic exploitation on CGC, and a follow-up, will there be another live stream on fuzzing plus SMT solver symbolic execution? So I didn't go to Tyler's talk. I don't remember why. I wanted to go really badly, but there was some reason I couldn't attend it, so sadly I wasn't there, which I'm kind of sad about actually. I've heard it's really great. About the follow-up question, well, probably not now, because I'm somewhat familiar with how fuzzing and SMT solving works. I did have some attempts at it. I don't know how to do it in a good way, so I will probably not do a live stream about it. Maybe someday in the future I can do, however, a live stream about like SMT solving. I'm not an expert on it, but I do use it sometimes on CTFs nowadays. Like in the past I wasn't using, but recently I am using it. So I did a live stream on Polish actually to show some like how to solve the KrzaQ using SMT. I guess I can redo it in English because why not? It was quite fun. So yeah. And about symbolic execution, concolic executions are not the subjects which I'm an expert in, so I probably am not going to stream about it until I learn them enough that I can explain them to somebody. What's my origin of my nick? I guess Gunvale came from The Witcher, but Coldwind. That's correct. Gunvale came from The Witcher, from the books when I was in, I think that was still the elementary school, like the late years of elementary school. I read The Witcher books. They were like a super hype in Poland for The Witcher series. It was like, I really like the books. So yeah, Gunvale was the name of a town in like the second volume of short stories from Witcher. Now, Coldwind is actually a name created from the Dragonlance saga. Basically, the Dragonlance is a pretty cool, it's an RPG system, but it's also a series of books. And every hero there basically had a name like Fireforge, like two-word names, where one was an adjective and the other was, So basically like Flint, Fireforge, Storm, Brightblade, and so on. So I decided, hey, so I'm going to be Coldwind. I needed a name for an RPG session, like a tabletop RPG. So yeah, and then Gunvale Coldwind, that's the origin of the name. That's the origin, yeah. There's another question on topic, actually. Can I quickly comment on when to use libfuzzer and over AFL? Libfuzzer is something created by the same people that are behind ASAN, if I'm not mistaken. Basically, libfuzzer and AFL are somewhat similar. I guess AFL has the same features as libfuzzer has. So libfuzzer is something you actually use for in-process fuzzing. What's in-process fuzzing? In-process fuzzing is so the way we do it here, right, in my dump fuzzer. So this is not my dump fuzzer, this is my dump fuzzer. What I do is every time in a loop, I restart the process, right? And this is stupid because executing a process takes time. What AFL does by default, it uses something called a fork server. A fork server is basically, it starts the application once and does inject some code there, and the code basically listens for communication from AFL itself, right? And if AFL says now, what the process does, it does a fork, and it launches the fork, and the fork does the actual, running the application. Forking on Linux is faster than executing it from the scratch, because forking does copy and write, so it doesn't need to allocate memory, copy memory until it's touched, and so on and so on. So it's actually faster than executing the process from scratch. And then, AFL just says like now, and it just fork, and it executes the application again and again. Now, what you can do also is you can do in-process fuzzing, which is something that libfuzzer does, and it works like this. You basically create, you do need to do it manually. You take the application and you put main function in a loop. So you don't restart the application once the main is finished, or whatever function of the library you want to trigger. Usually write the main yourself, and it's rather like initialize the library, load something, and like deinitialize it, or even initialize it at the beginning, and then in the loop run the library function on new data each time, like forever and ever until the application crashes. And actually AFL can do it now as well. At least that's what Elkamtav said on my Polish stream a couple of weeks ago. What's the advantage of this and what's the disadvantage? I guess there are currently no disadvantages of using in-process fuzzing. And I'm saying currently because historically you had problems with using it because, if you have a bug which doesn't crash the application, but it actually corrupts the state of the application enough that in 2 or 3 iterations of a loop it actually crashes, then you catch a sample and you say, haha, the sample crashed my application. But that's not true. Actually, the sample which corrupted the application was a sample you ran like 5 times ago. And there are different works around for it, like you kept like 100 samples back, or you actually used a pseudo random number generator. You kept the seed of it, so you knew how to regenerate all the mutations. and find one which actually does like find a pair of mutations which actually run one after the other, could crash the application, so on. Now you don't have to do it because of ASAN. ASAN, which is address sanitizer, if you compile it with your application, it actually does detection of memory corruption, and it does it in a really good way. So you don't have to worry that, oh, this sample will corrupt my heap, but only the next run will catch it, because ASAN will catch it when it corrupts the heap. So that's actually a really great tool. Now ASAN isn't like bulletproof. There are, if you know how it works, it's basically quite obvious that there are cases where ASAN will just not catch it. But yeah, it's basically a really good tool, and due to the awesome detection it provides, you can use in-process fuzzing safely without missing too many samples. So I guess that's in-process fuzzing, and again, both in libfuzzer and with AFL you can use it. Now I believe libfuzzer and AFL actually differ in the mutation strategies they use, but they differ in implementation, but I guess the idea is behind them is the same. Now, in case of fuzzing, using two different implementations which do things a little different, it's beneficial. Use both. Basically that's the answer, because one implementation might, due to some quirks in it, might actually reach a state that crashes the application while the other implementation doesn't. That's true for all fuzzers. That was actually a really good question, by the way. So thank you for asking it. You should have bought Ryzen 7 instead of i7. I actually like Intel, so I'm sticking with Intel. I know how it works basically, and yeah, that's the only reason why I bought i7. And I also didn't buy the newest CPU. The newest Intel CPUs don't have. There isn't the Extreme Edition yet, and I like the Extreme Edition since they usually like add some more cores or something else. So yeah, I like using HXD. HXD, I believe, will be a hex editor. Do I have a browser? Let's look for it. Free hex editor and disk editor. Oh, it looks much more advanced than Hexplorer, which I did show you. So yeah, like HXD, that's a recommendation from Niemand. I actually need to check it out later too. Okay, then Piomar123 says +1 for that same hex editor. Have you used Manticore before? What's trail of bits Manticore on GitHub? Let me look up what is it. It's a question from Philip. I have not. No, I have no idea what this is. Thank you for sending me the link. I'm going to actually note it and check it out later. Okay, and one more question. Can we use the CFG edge path tracking with libc functions as well? Okay, I kinda know in theory how CFG works. I don't know the implementation details. I need to take a look before I can answer your question. It's a good question, but I don't have an answer which I would be sure that it's correct for you. So I'm sorry. Yeah. I guess in theory, I don't see why not, especially except for some edge cases. It might mean you'd have to recompile your CFG though. Okay, so I'm going to I'm going to tell you now how to how do you usually implement genetic fuzzing. I'm not going to implement it today. I'm going to implement it next week because, well, again, because I'm talking so much, I did run out of time again, so I'm sorry about that. What do you need? You need basically two parts. The first part is called a tracing instrumentation, or just tracing. It's basically a part which, when you execute an application, it tells you the application executed this instruction, this instruction, this instruction, and this instruction. Now, what's the easiest way to do it? I guess AFL does it in a pretty smart way. Let's compile this like ASDF .c again, but I'm going to do -mas intel -s, which actually just generates the assembly code. Now, I don't know if you know, but GCC isn't a compiler. GCC, like the executable itself, it's so-called a driver. It drives the compilation, but it actually uses a set of tools to do the compilation itself. It first runs something like called CPP, which is a C preprocessor, which does the preprocessing, you know, includes, define, and so on. Then it actually uses something called CC, which I don't have it in my path directory, maybe CC1. Yeah, I don't have it either. It's basically the C compiler, which generates, what does it generate? I believe it generates assembly or it can generate assembly. It doesn't have to, but it can generate assembly or an object file. And then if you have assembly, you can use AS to basically, which is the assembler, which gives you an object file, and then the object file is linked by a linker, right? And GCC actually does this, like calls all these applications for you to make your compilation easy. Now, what AFL does is it basically jumps into the after generating the assembly, right? But before actually assembling it, so this is our application, right? And it looks for basic blocks, and this is a basic block. Like it's easy to tell where the basic block ends just because there's a jump instruction there. So this is the end, this is the end, this is the end, this is the end. Sometimes in some implementations of everything, of tracers, of everything, call is also treated like the end of the block. Personally, I never treated call as the end of a block, because in C programs, call is supposed to basically return, either not return at all, or return to the exact same place. But you can treat also call like a new block, so you can treat this as a new block, or you can actually, I'm sorry about that, or you can actually treat this whole thing as a block. Now, for each block, it would actually add some code at the beginning of the block, so that would be, for example, here, right? And the code would actually just mark that this block was executed. And so this is the basic implementation. I'm not caring about edges right now. I'm caring only about nodes and only about basic blocks. Node and a basic block is basically the same thing. It's just, you know, the block in IDA, right? And IDA also doesn't think call ends a block, by the way. And the code which is added here, which I'm going to add next week, I'm going to actually write a Python script probably which does it, is just, hey, mark that this block was executed. And it can be done in a couple of different ways. The easiest way is probably like move and now some, and this is pseudocode which I'm writing, is not proper assembly, obviously. Like global memory, like global shadow memory, plus rip minus like the offset, start offset. Yeah, 1. Or you can actually do, yeah, I guess that's okay, like byte. Now, what's shadow memory? This isn't the best way to do it, it's the fastest way to do it. You basically, at the beginning of the application, you add something that before main and before all the other code is called, creates like maps a block which is the size of the application image. So the application image in this case is what? Is like 50 kilos or something, right? Yeah, but that's not true. Strip A. Yeah, it's like 16 kilos, right? And that's like including the data section, but the text itself would be 8 kilos or whatnot. That doesn't matter. You can allocate like including the data section. So anyway, I'm going to do something like this. And you have the application placed somewhere in memory, and then you, in another place in memory, allocate the shadow memory, which is exactly the same size. And then when you reach this point in the application, you mark the exactly same position as in, you know, like position from the start in the shadow memory. And then you when you reach each of these places, you mark it in shadow memory. And now when the application leaves, because we care about the coverage only when the application does not crash, so it leaves correctly. We basically go through this memory and like grab all the locations which are marked as I have visited here, and the mark it as 1. Now, this uses a lot of memory because for each byte you need to have like a byte here, and there might be some caching issues as well. So a better way to do it would be actually like to know how many basic blocks you have, right, in the application, and actually allocate only a small space of memory to totally ignore the instructions, because, you know, this instruction, for example, here would be never marked because it's not the beginning of a block, right? So yeah, so you just like ignore them totally, only focus on the ones which you can actually reach, and that would be way less memory. And you could, like, if the application reaches here, it would be actually this one, like this one here, and if it reaches like the next one, it would mark the next bit even, and that would save a lot of memory. It would also, the caching issues and the speed would be better. So that's another way to do it. And this also gives you uniquization, which means that if you visited this node once, you don't have it twice on your list, because another way to do it would be just to add to the list, add the node to the list, to the list, to the list. That's great for tracing, but not for tracing in the way we need it for fuzzing, because we just need basically the list of visited nodes. So this is the first thing. You need to either implement an assembly snippet. If we would actually implement this here, right, I would write some code here, then I can compile it using basically like GCC AS and this, why do you not like me? Oh, because it's ASDF.s, and GCC would compile it including all the code changes which I did. Now, if you don't have the source code, you can still use any method of tracing which you know, which could be anything from using DynamoRio, Intel Pin, or just putting hooks by yourself in the application. This is usually quite fast. You can also use a debugger and set breakpoints, like temporary breakpoints, which is like tbreak and GDB, which are disabled after being hit once, but still leave a really nice list of all the places which are hit. And you just grab that list, and it's also coverage information for you, right? Or you can compile with address sanitizer, and address sanitizer actually will give you a nice list of coverage. Now, I don't know, let's see if I have address sanitizer here. Let me switch to CLang. And I never remember how to actually, like, CLang address. Wow, CLang 5, there's CLang 5 already, I didn't know that. Okay, so it's like, I know this. Sanitize address, so that's one thing. Okay, so CLang, I do have it, so I'm going to compile this with f sanitize address, and I also need to do something like ASAN coverage. And yeah, and we're going to sanitize at basic block level, which is the same as graph or the same as whatever. So I'm going to compile it. It doesn't like this. Did it? And the linker doesn't like me. Why doesn't linker like me? Okay. So it doesn't seem I can use address sanitizer here. Can I use it on Linux at least? Oh, perfect, I have this, so I'm going to try to compile it on Linux. Maybe I can show you at least that it does generate the coverage. Okay, yes, perfect, generated, which is good. Okay, and this is perfect. Will be deleted. It actually removed my buggy code, because in C and C++ implementation, it's an undefined behavior, and the compiler can basically do whatever the compiler pleases with undefined behaviors. So yeah, so now I have this A-out, which is my application. It doesn't do anything, right? It just like returns some error code. I do need to pass it some arguments, so let's pass it an argument like input sample actually, but that doesn't matter. And it should like just return 0, which is okay. That being said, I'm just going to take a quick peek at the application, and maybe not in IDA. Let's do object dump -d A-out to see if, whoa, this is a lot of code. I hope it didn't run the dead code elimination, because then it would just eliminate all my code, but that doesn't matter. Now I'm going to do asun set an environment variable called asun options verbosity equals 1, just to check if it works. It works. As in, you can see that if this is okay, you can ignore it. asun was run indeed. So now I need to do coverage equals run coverage, yeah. And it did write a file which has a suncov, like sanitizer coverage extension, and it written how many basic blocks did it actually visit. It visited 3 basic blocks, which is, if we launch IDA, that actually sounds fine. This is 1 block, 2nd block, 3rd block, and then it went somewhere here. So maybe it should be 5 blocks, but that doesn't really matter. And what I can do now is I can actually write, well, show you the file. So let's do hex dump -c, and the file is a out, then the 566 is actually the PID. And this is some magic value, if I remember correctly. You can ignore it. And then there are the offsets of the basic blocks which were actually hit inside this application, right? And yeah, and if you would actually go to IDA, I'm going to rename this maybe. Okay, I'm going to load it into IDA. And I'm going to go to the specific offsets which were printed. This is, for example, 4E73, so 4E73 9F. Yeah, and it's where are we? Because as you can see, Address Sanitizer actually added this instrumentation which I was talking about here as well. So it has like, I have absolutely no idea where are we. It seems we are somewhere at the beginning. No, we are in the main, right? And then there's some Address Sanitizer stuff, and this was hit. We know this was written out. And then this is before opening the file, so this is probably just telling us that it did hit this block. Yeah, this basic block. But that doesn't really matter, because usually during fuzzing you don't really inspect the application. You just need these like addresses, right? And it has 3 addresses. And if I would, let's for comparison, now I'm going to change this to BC. So I did, these 2 letters are correct now, right? And I'm going to run it again, and it will generate a new coverage. Oh, it did only 3 blocks because I didn't put the proper file here. So I'm going to change it to AAA again. Its test file. It has written 6 PCs now, but if I do BC here and I run it again, it's 10 PCs now. So, my fuzzer needs to basically read this list, check it against a list of known basic blocks, and then if a sample is not on the list, it needs to add it to the input corpus, and it needs to obviously randomize whichever sample it picks from the input corpus, not only use the one which is provided at the beginning, right? Yeah, and basically with each more basic blocks come with each letter guessed, and then at the end it would have all of them and the application would crash. So yeah, that's the theory behind this. Now if there are any more questions, I'm going to answer them, and then I'm going to finish for today. Again, at the end of the stream there is a small challenge for you guys. Now let's look at the questions. There's only 1 question, so this will be quick. I think the IDA approach is pretty cool if you know how to script it. I'm not sure what you mean by the IDA approach. That being said, IDA scripting, yeah, basically like scripting of everything that includes like GDB or IDA or any other tools which it's a cool thing to know. I mean, scripting at debugger helps both in like real-world applications and when doing CTF challenges, so there's no question to that. That being said, I'm not sure what you're referring to. Basically, when you're asking questions, make sure to give me the context, because if I I like go with the flow of the words for half an hour and then I look at the question, referring to something I said like 20 minutes ago or 10 minutes ago. I just have no idea, so I cannot answer the question. I'm really sorry about that, but yeah, it's like how I work. I'm sorry. Is there a chance you're going to talk about shadow breakers? I was supposed to look into this topic. I'm not going to talk about it today. Maybe I will be able to look into the topic for next week. I'm sorry. I know I told you guys last week that I will look into the topic, but I was not able to do it yet. Yeah, sorry about that. Let's see. Any more questions? If not, then we'll round it up for today. I guess shadow brokers, yeah, not breakers. So I guess that's about it. Therefore, thank you very much for being here. Thank you to KrzaQ, who actually helped a lot today. And yeah, that's it. So see you next week, and we'll implement this genetic fuzzing then. And if you have any ideas for what then we can talk about after fuzzing for, you know, in 2 weeks, then just let me know. So I'm leaving you with some music and with the challenge which I promised you. So thank you very much, and see you next week, everyone. Have a great evening, day, or whatever time is in your time zone. Bye bye.